Okay, so I just put together some of the questions that were discussed, and in a common umbrella, it's recorded. So if many of you just want to solve the problems and not listen to the previous talks, you can just come to this. I also have some of my own favorite questions here. You know, that's the reward for organizing this. So the outline is the following. We'll talk about fine-grained complexity, like gap ETH and exponential time. Instead of polynomial time, like NP versus P, will be more fine-grained. But then people don't really consider that fine-grained enough. So the second fine-grained, we'll talk about n to the omega k type lower bounds. But people consider that parameterized complexity. And then the real fine-grained. So that's the outline of the talk. So problems in fine-grained complexity. So it's just this one slide. So yeah, the first question is, does ETH imply a gap ETH? So this amounts to creating a gap creating reduction, and we want to do it without building a linear sized PCP, because that's not fun, right? Like, you want to really use the fact that you have exponential time and you want to do very little blow up. So there is this time versus blow up sort of thing that we want to exploit better. The only serious attempt without building a efficient PCP is by Benny Applebaum in 2017 using smooth ETH and so on. That's the first one. Does Seth imply gap Seth? So it's like an even stronger thing. I actually think that gap Seth might be true, but we shouldn't be able to prove it using Seth. So maybe one can try to falsify a notion of a reduction. So assume there is a reduction from Seth which magically just blows up by 0.1 variables and creates a gap. It should falsify something. You're just creating too much. So that's the other question. Then I just came up with this thing, big gap ETH. It was known in the community, but let's just concretely formulate it. It's gap ETH, but in the soundness case, you have epsilon instead of 1 minus epsilon. You get something directly from known reductions, but is there something non-trivial that can be known? And it's not like it's a made up, like a very hard to believe thing, because we can, instead of 2 to the n, if you had n over polylog n, we can achieve this. So yeah, this is all in the small fine-grained world. Now we move to the uppercase F fine-grained world. Here we have, these are things that are not known under gap ETH. We don't have a tight understanding. There is set cover, biclique, densest K subgraph, 2CSP, and clique. All of this or subset of this was mentioned in the talks right now, but it's all in one place. And these are things, even when we assume a gap, we don't know how to do it. So these would be like the first things to try, the technical tools then we can use for getting it under weaker assumptions. Of course, once this is established under gap ETH, we would want it under ETH and corresponding W1 hardness and so on. So the same is true for ETH, but it's a smaller set of things because we dream less here. We don't even know constant approximation for biclique and densest K subgraph and so on. So anything here is like beneficial. Under FPT, yeah, like if you want W1 hardness, W2 hardness, yeah, we don't even know how to show like constant hardness for 2CSP and some polynomial factor hardness for clique, and set cover, we don't know anything beyond a constant factor for W2 hardness. So yeah, all of these are open. We are lacking mainly tools. We believe these are all true. So yeah, hopefully we can make progress on this in the next few years. Okay, let me get to the fun stuff now, the real fine-grained stuff. So let me start off with a question which Ligia had asked me in a coffee shop at some point. So whatever the distributed PCP things you saw, it requires that your n vectors are in log square n dimensions or less. Of course, if I tell you about the orthogonal vectors hypothesis and I tell you it's in higher dimension, like log cube n, it's more believable. But all of the framework completely just breaks apart when the dimension is log cube n or more. So is there a way to get the same conclusions we get from distributed PCP, but starting from orthogonal vectors, not in log n dimension, but polylog n, like larger log n dimensions. So that's the first question, because it's a more believable assumption. So you would want to have things under more believable assumptions. The second thing is there is this thing called hitting set conjecture, which is you're given two collections of sets, A1 to AN and B1 to Bn on a small universe, C log n, and you want to know if there is one set in the first collection which intersects with every other set in the other collection. And naively you can do it in n square time, and this is believed to be tight. This implies OV, and then we want to know how to get hardness approximation versions of this. As a concrete question is this one center question. You would want to prove this result, that given two sets of points, is there one point in one set that is close to everyone, or for every choice of selection of one point in the first set, it is far from one point in the other set. Is there a good one center or not? And again, the distributed PCP doesn't say anything here, and we would want to prove. And both are falling under distributed PCP limitations because the technique doesn't go through. But these are natural questions, like this is a classic question in clustering, like one clustering. Closest pair, given n points, find the closest pair. We don't know how to rule out n square n to the 1.99 time algorithms, which 1 plus delta approximate. The current lower bound is like n to the 1.5. So we would like to show that there is nothing better one can do these things. So this is another classic problem for which we don't know things. Okay, so this is an email I got from Avyad 4 or 5 years ago. I was quoting what he wrote exactly as he wrote it. He says that if I tell you find a triangle in a graph and I promise you there is a large clique, can you use this information in any way? Or is it as hard as finding a triangle in an arbitrary hard instance? Right? I'm telling you there is a clique of size log n. Find me a triangle. Can you do this somehow faster? Or does it not at all help that there is a log n sized clique? So if you want to believe that it doesn't help, that means that you start from a graph in which either there is a triangle or there is not. And if there is no triangle, after the end of the transformation, there is still no triangle. But if there was a triangle, then suddenly now there is a clique of size 100. So it's an amplification in the completeness case, which is sort of not common in hardness approximation. And yeah, Amir had told me about this question, the second one, many times, that apparently it's common in the vision community that either you're given set of n points and either no three of them are on a line, or there is one line that sort of fits many points together. So this is just this, in regression this is very common, like fitting it to a line. Now can you find that line? Finding that line just amounts to finding 3 points that are collinear. So you would want to start from the case where either there are 3 points collinear or not, and then amplify such that if there were no 3 points collinear, there are still no 3 points collinear. But if there are 3 points collinear, suddenly now there are 100 points that are collinear on the same line. Now then there is edit distance. Given two strings of length n, can you rule out subquadratic algorithms that approximate it to any 1 plus delta factor? Yeah, I don't even know how to do anything here, but it's there. Again, one more question from Amir's talks is triangle detection easy when the even girth is large? So it's if the graph has C4 free and you want to find a triangle, can you do better? Like, can you do faster than naively the best triangle detection algorithms using the information that the graph is C4 free, C6 free, C8 free, and so on? I think Amir has a paper when it's C4 free, but you would ideally want to say it for all C2K free. Okay. Did you mention this OMV conjecture? Okay. This is a classic hardness approximation question. So there is the OMV conjecture, which is just saying you're given a matrix, Boolean matrix, and you're given a sequence of vectors v1 to vn, and you want to compute the product, but sequentially. You cannot compute MVI before you compute the previous MVI minus 1. And this requires some this requires cubic time. And the approximate one says you don't need to compute the exact answer. You can be off by some factor, n to the 1 minus delta. Can we start from the one without the gap and prove this version? Right? And the reason I like this is because matrices, particularly Boolean ones, it's very natural to just take an error correcting code and apply them, and it automatically creates a gap, and you just have to decode. But the product here is Boolean product. It's ors and ands, not over a field. So that makes things messy. Okay, this was a homework in my graduate course, but it's a very hard open problem. So from now on, the problems get harder. I want to compare set and unique games conjecture. So under unique games conjecture, we know vertex cover, there is no polynomial time algorithm which 2 minus epsilon approximates it. Okay. Can we use the power of exponential time, set, and everything? I just want to rule out subquadratic algorithms on sparse graphs. Okay. And I want it for a factor 1.5 because square root 2 we can rule out polynomial time under NP not equal to P. So give me something better than NP hardness, but using set, not unique games. Again, the whole point of this is not because this result would be interesting, but the proof would help us understand how to use the fact that you have so much space, so much time to play with. So I don't really care the theorem that you would prove from here, but rather how you prove it. So this is the other thing, trade-off curve for petas. So suppose there is a problem which is NP hard, but there is a petas for it. Okay? So say there is like a 2 to the 1 over epsilon times n algorithm. In literature, there are lower bounds saying you cannot get an algorithm that's better than this dependency in epsilon. But these typically say, suppose there is an algorithm which for every epsilon does better, then I'll find an epsilon for which it contradicts ETH. But that's not satisfying, right? Like, what if epsilon equals log square n, 1 over log square n? Then this algorithm runs in time n to the log n. But is that tight? Can it run in time n to the log n? So you would want to prove a lower bound for every epsilon between constant and 1 over n. And the concrete candidate is 1 center. Is there a question? Yeah.
Can you do some padding?
Yeah, so this padding sort of loses a lot. I thought of what you would ideally want to do is start from exact version, then create a gap using some direct product thing. The blow up in the instance with the gap you generate sort of match one another, so that when you create a complete gap, it's exponential size, but just enough, like there is a perfect nice trade-off. But that would be a very nice thing to do. All along, you're still in the 1 center instance and blowing up. I can imagine those things for MDP or like tensoring that works, but like maybe 1 center, I don't see how to do it. Okay, so this is one. Yeah, so this Amir mentioned. This is known in the community at least for a while now. Take an NP hard problem, your favorite one, and we know it's NP hard for factor alpha, but anything beyond alpha, it's in P. And people say, okay, we are done, and we move to the next problem. But let's not move on. Let's not settle until we show linear time. So for alpha plus epsilon, it's in P, but it would be interesting if you can show a quadratic lower bound in the input size. Then you would want to find what is that alpha plus epsilon for which it's in linear time. So you'll have a very fine-grained understanding of what's happening, or you'll eliminates the hardness of the easy instances. Even within P, how hard they can be, even though they are in P. And I don't have a good candidate. Every candidate we tried, we came up with linear time algorithms. So it would be interesting to just come up with something to begin with. I think Amir mentioned Steiner tree as a candidate. Okay, so let me say something very controversial now. Right. But somehow, like for instance, clustering and all these things, you would guess that, but they come up with some greedy thing which is very efficient. You can always replace it, like, right? You need to prove a lower bound that you cannot do better.
No, if your best algorithm is a penalty-based.
Sure. Then, yeah, then you can, that's a candidate. But, yeah. But I don't know if we can prove, but proving this sort of, you understand it even better than just showing it's not NP hard.
And then also, I think, because like we are like finding using multiple substitute factors, I think solving LP or SCP can be like usually done in linear time.
Right.
That's another.
Yes.
So actually for this problem, like, does it also apply to those that have tasks? If you have a task that runs n to 1 over epsilon, right? And those, like, typically we know that you can get efficient tasks. Like,
Sure, yeah. But those algorithms, okay, that comes to the previous thing, right? The way you typically prove it is, suppose there was a better one.
No, yeah, I totally understand. But I'm saying, like, those, do you consider those also candidate for this solution?
No.
Those are not.
Yeah, those are not. Like, I'll give you a non-candidate, but would have ideally been like a nice candidate, right? Suppose vertex cover, the two approximation was not linear time. Suppose, matching is all not linear time. Then that would have been a nice candidate. Like, I can do two approximation, you prove some lower bound, which is quadratic or cubic or whatever. 3 approximation is linear. Like, yeah, those are the kind of problems. I don't know any problem of such importance or ubiquity.
I think I have one candidate.
Nice.
It's just low degree spanning tree.
Uh-huh.
Like minimize max degree of a spanning tree.
Okay, and what is known?
What is known is that you can get additive one approximation
Uh-huh.
in mn time.
Okay.
And people try to improve running time. We failed. So
I see.
That one might be okay, but it's like extreme point here. So if you're wrong, you got to be really exact.
Right. Also, additive is a bit harder to handle. I don't know how to.
Actually the algorithm in the weighted case used iterative routing, but the unweighted case is completely combinatorial.
I see.
And yeah, it could be.
That's a good, yeah. Whenever it's combinatorial, it helps in proving lower bounds.
Yeah.
What if you added +2 +5? Does it become easier?
We don't know.
That would also be nicer to know. If it's plus 10 and it's linear,
It's like linear or
then we can try to prove some. Yeah.
If you allow log n multiplicative approximation, then we can get fast algorithm, but like constant multiplicative approximation we don't know.
Okay. Okay.
Yes, we kind of augmenting parts, something like that.
Just for the video, Touchaphone said something. So if anyone in the future wanted, you can email him. Oh yeah, controversy, right. Yeah, so my controversy is people do believe that NP hardness reductions are the gold standard, and so this is where I will like to disagree that the self reductions are the gold standard. Why believe P is different from NP? The best reduction would be, I assume some problem takes whatever time it takes, and then the approximate version takes as much as the exact version of the same problem. You need to be completely independent of other problems. Just create self-reductions. And until you get that, you shouldn't stop. So even, in an NP world, you can keep doing this thing. Do a self-reduction from clique with no gap to clique with gap, set cover, everything. So for instance, CSP is a self-reduction. So that we have. But yeah, we can do that for every problem. Then you don't even really need to make a hypothesis of how much hard it is. It is as hard as it is to be exact, that's all. So that's the gold standard. Yeah, that's it. Now anyone can come and take the mic from me. Whoever wants to speak next.
A candidate for the between the feedback access or weighted current
I have no idea the problem.
so
Too many variables.
so like you consider the feedback access problems on the weighted current. So there is a pretest for that.
It can be, but you have to really, the whole point of this thing is to understand the structure of the whole problem, and you want to keep creating the gap every time. So whichever problem for which you have a technique to amplify it. Someone, Saket, you want to?
Yeah, very good. If some other people want to go.
I think they're all waiting.
Okay, so I think in the vein that you asked the question, so I have two questions. So I don't have slides, but like, okay, let me try to write it. So in the FPT world, now at least we have started to come up with problems for which, say, for example, so let me give you a very concrete problem so that at least I can, so I don't know whether it is possible to improve or not. But let's say distortion or many other problems for which we do know that there is a lower bound of, say, form k power k. I mean, you cannot do, so you have a running time for exactly, and you cannot have an algorithm with running time k to the power little of k. For example, distortion is one problem, distortion to line. So for such a problem exists. Now, is it possible that either we can show that it has some, so for this problem, maybe I don't know whether it exists or not, but even a constant factor approximation, you cannot exist in, say, c power k time, for example, right? Or like there is, so there is like some approximation that if you wanted to have this kind of running time, then it is not possible to do, right? So can I show that for distortion, there exists some epsilon greater than 0, such that 1 plus epsilon approximation is not possible in, say, some FP, say in c power k time or some c depending on epsilon, right? So it's a very concrete question. So I give you a distortion for which there is a d power d algorithm, k power k algorithm. So distortion is basically you're given a graph G. You want to place the vertices on the line so that for every pair of vertices u and v, the shortest distance is same as in the graph, but in the line they have not been distorted more than factor d. Okay, so that's a distortion. So unlike bandwidth, this problem is FPT parameterized by the distortion, and there's a d power d algorithm or k power k algorithm. And we showed it later that this is an optimal algorithm in the sense that if you want it exact, you cannot beat k power k. But now if I allow you power of approximation, it's possible that you might be able to beat this running time. I haven't thought about it, whether you can beat or not. But many times it does allow, for example, directed feedback vertex set, you can get a c power k running time and get a factor 2 approximation. I don't know how to beat that, that's a different question. But is it possible for us to prove that for such kind of problem for which exact has some sort of running time lower bound, and if we can say, if you wanted to do approximation, you shouldn't be able to do too much better, like in c power k. So it is in the same flavor as you were asking in the p time world. Maybe in this world, things are different, so maybe you will able to show some lower bound. Yes?
Is there any problem for which you can answer that question? Yeah?
No, I don't know. This is exactly why I posed this question. And I think distortion is a good candidate. Or some string version of the question could be a good candidate. But the problem with many of the string questions are, they're FPT, but they also have p tasks, so then it becomes very difficult to understand them. Okay? So we had this paper called K power K some 15 years back, where we framed many of these questions, and we showed concrete lower bounds, but it would be nice 2 decades later that try to prove some of such kind of statement. So that's the first question that I had. So it's like a methodological question. And the second question is like a cry from the FPT community. So I'm going to tell that. So for many of the hardness that, okay, I'm an engineer, I'm not a theorist like you. So from engineer's perspective, we start to show hardness. And many times we show hardness from, so like a version of PIH, which is for 3 regular 2 CSP, or like bounded CSP. So let me state. Okay. So there is a, so all the time we say, this is a theorem that we state. Unless ETH fails, right? There is an absolute constant epsilon greater than 0, and that is my epsilon greater than 0, such that no algorithm takes as input g comma k of 3 regular 2 CSP instance with k variables over n size over size in alphabet runs in f of k n to the power big O of 1 time and distinguishes whether it is fully satisfiable or like fully satisfiable or at most 1 minus epsilon satisfiable. Okay. So the problem is that whenever we get many of these reduction, I don't know what this epsilon is. Can we quantify this epsilon? It's like this epsilon is at least 1.005.
That's very hard.
I don't think it's that hard. At least I tried to trace. So like it's in the mess of like some what do you call expander constructions and this and that. But like it doesn't look that.
You just want any epsilon with
Like yeah. So but give me 1.00001. I'm fine with it for now.
that's fine, that you can do.
Yeah. So but like I don't have like the injured, but I tried to trace. It took me 3-4 days, and it looked it is possible, but I didn't know the best construction of many of these things, so I left it.
Just
But
depend on the best 3 regular expander.
correct, right? So can we compute this? Because I think if you give this, it will help the field grow because then you will start to get numbers, and people will start to make an algorithm which will try to match them. At this point of time, yeah, I cannot do this, but like what I cannot do and what I can do, we still do not know how to fight with them. Okay, so this is why I say it's a cry from people who are doing algorithms. Okay, you give me this, I will give you something else. Okay, so for example, we were doing something and like we got an approximation 4/3 and like yeah, but what's the lower bound? There is some 1.001 that we cannot do it. Fine. So it just helps us distinguish between whether a problem has a parameterized approximation scheme or not. That's it. But like it's like a APX hardness result. There is something that doesn't happen. But if we can trace that, and then my feeling is that for many natural combinatorial problems that we see in parameterized complexity, you will see many more results, people proving that. So that's my second question. What is this epsilon?
Okay, by email is fine.
Huh?
By email,
What?
the proof of that.
Anything is fine, right? But like it should be written somewhere.
Yes, fine.
For other person to use it. Like, so last year for a week, I did spend trying to trace out. It didn't look impossible. That's all that I'm saying. It's like, but I still don't know what the right things are. Okay? So these are two questions that I had, which I wanted to pose. So thank you.
Anyone else? Touch your phone.
Okay, so just like this. Okay, so tomorrow I will give more context about the question that I will ask now, but here's a question. You have a matrix and you want to compute the rank. Well, we know how to do it in into omega time. Can we approximate this rank faster? That's the question. And yeah, clearly this is fundamental, and just gonna give some more context about flow problem tomorrow.
Can I add something to that?
Yes.
So like, even the log n approximation to that question will have a lot of bearings if you do it sub-quadratic.
Is there any interesting thing you know about approximation?
I don't know anything. Yeah.
This is a question which I posed 2 decades back in one of these contests. Because it has a relation of computing representative sets in parameterized complexity very fast. So it's possible that for many of these questions like Hamiltonian paths and cycle, you might be able to beat 2 power n if you could do something like this. Right? So that is
So wouldn't also this give a natural way to prove lower bounds then? Assuming those things cannot be done, right?
Yeah. So this is the reason why we were interested in, like, around 2014 or something, we tried, but nothing was going to be observed.
Next question. Not me.
Anyone else? Anyone else? Okay, so we call it a day then. See you all tomorrow.